Okay, so far we have seen examples where we constructed the exponential generating functions from some things, and we found hns first, put them into my function, or used the formula, and got things. Now let us try to work the other way. Let us do some examples where finding hns can be relatively hard. Instead, the exponential function is really easy to get, and that allows me to find my coefficients much better. Okay, so that it gives us a use of these exponential generating functions that we have been trying to do so far. So let us look at example. Let hn is equal to number of n-digit numbers, n-digit numbers with digits 1, 2, and 3. And these are the only ones that I'm allowed to have, with 1 used even number of times. Even number of times. Well, I have to figure out how many ways are there of writing some n-digit numbers with just the digits 1, 2, 3, and n is used even number of times. So, answer. Observation. First of all, observe that hn is basically number of permutations, n permutations, number of n permutations of the set infinity times 1, infinity times 2, and infinity times 3. Right? Each of these have infinite repetition allowed with 1 used even number of times. Even number of times. Well, I have already seen how to do this from previous example, right? The one which had the complicated formula with fn's, and I know that the generating function I get there, regardless of whatever hn is basically 1 plus x squared over 2 factorial plus x to the 4 over 4 factorial plus dot dot dot, since I'm only allowed even terms for even number of ones, times 1 plus x squared over 2 factorial x over 1 factorial plus dot dot dot, which is basically e to the x for the number of 2's, and 1 plus x squared plus over 1 factorial over 2 factorial dot 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 for the number of 3's. Oy, oy, oy. Okay, great. Then, this I can realize, well, all my odd terms are missing, right? How do I kill my odd terms? Well, if I had the odd terms, that would have been e to the x. What I can do here is say, hey, this is e to the minus x over 2, right? Because if I had e to the minus x, it would have 1 minus x over 1 factorial plus x squared over 2 factorial minus x cubed over 3 factorial. So if I add e to the x and e to the minus x, it cancels all the exactly odd powered terms, leaving the even powered terms twice, so I have to divide by 2. This is e to the x, and this is again e to the x. So all of this is equal to e to the 3x multiplied by, plus e to the x all the way over 2, right? Which I know is equal to, since I know what the expansion for each of these is, 1 over 2 summation n is equal to 0 to infinity. E to the 3x is 3 to the n x to the n over n factorial, plus e to the x is summation n is equal to 0 to infinity 1 to the 1 times x to the n, well, whatever, 1 to the n, x to the n over n factorial, which is equal to summation n is equal to 0 to infinity 3 to the n plus 1 over 2 x to the n over n factorial. And that means that if this is my general exponential generating function, then whatever I have here should be my hn. Therefore, hn is equal to 3 to the n plus 1 over 2. And so even though my original question was complicated and I didn't have a really good way of finding it, maybe I could have struggled through a lot of, maybe, let's say, dirt to find the answer. It is possible I could have used some arguments properly and tried to find it. But this is a much cleaner solution, right? I know my general exponential, I hate when it does this. I know my exponential generating function in this case, and I can use that to solve my question, right? Okay, let us look at one more example of this kind. Example. Suppose hn is equal to number of ways to color a 1 cross n chessboard with n colors. To color not n colors, we color 1 cross n chessboard with red, white, and blue, and I have some condition such that first, number of red squares is even, number of red squares is even, and there is at least one blue square. At least one blue square. Okay, so I am looking at this. Find hn. And once again, this is going to be painful to find it just like that. So we are going to say I am going to take the longer way, in a way, roundabout way, and use my general exponential generating function. I know that my exponential generating function, similar to the previous case, is going to be, if I'm only allowed, okay, let me say this before. My exponential generating function is again based on the set infinity red, infinity blue, and infinity white, where and my hn is equal to number of n perms of S, where r appears even number of times, even number of times, and blue appears at least once. At least once. Okay. Then, once again, from my previous, as similar to my previous examples, I know that my exponential generating function, yes, I said it correct. Yes, my exponential generating function is going to be, for red, since it appears an even number of times, similar to the last time, x squared over 2 factorial, x to the 4 over 4 factorial, plus dot dot dot, multiplied by, for blue, since I have to have blue appearing at least once, it is going to be starting at x plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot, and white has no conditions, so it is my standard 1 plus x squared over 2 factorial plus dot dot dot. This we have seen before is e to the x plus e to the minus x over 2. This is equal to e to the x minus 1, and this is my nice and easy e to the x, right? All right, and so the product of all of these is e to the 3x minus e to the 2x plus e to the x minus 1 all over 2. Well, you know how to do this exactly from the previous, similar to the previous thing. You can work it out as this is equal to negative 1/2 plus summation n is equal to 0 to infinity 3 to the n minus 2 to the n plus 1 all the way over 2 x to the n over n factorial. Okay, I have all my h of n except for n is equal to 0. What happens at n is equal to 0? H of 0 is equal to negative 1/2 plus 3 to the 0 minus 2 to the 0 plus 1 over 2 is equal to, well, 3 to the 0 is 1, minus 2 to the 0 is 1, so those cancel. I have negative 1/2 plus 1/2 is equal to 0. Therefore, my sum h of 0 is equal to 0. I get g e of x is equal to summation n is equal to 1 to infinity 3 to the n minus 2 to the n plus 1 over 2 to the n factorial, and therefore hn is equal to 3 to the n minus 2 to the n plus 1 over 2 or 0, n greater than 0, n is equal to 0. And that is a good way of writing my values, even though I don't need to solve it completely. Okay, so I'll stop this part here.